we will study the different types of Lewis-base ligands and their bonds to a metallic center, explaining the organometallic complexes with Lewis bases. We have to remember the principle of polarizability. Consider, for example, a bond AB. This bond has ionic character and covalent characters, and the sum of the ionic plus covalent is equal to 100. Suppose the electronegativity of B is greater than A, so we have A plus, B minus. A plus ion will attract the electron on the negative ion B minus, and at the same time it will repel the nucleus. The negative ion B minus will also polarize or deform the positive ion, and in general the anion are large, cations are small. If the degree of polarization is small, that means if the degree of deformation is small, the bond is largely ionic. And if the degree of polarization is high, so we have concentration, high concentration of electrons between the two nucleus, and in this case we have large degree of covalent character. The polarization depends on two factors: the size of the ion and the charge of the ion. So we have in general rules to be followed, and these rules, for example, the small positive ion favors covalent bond, favors covalency, and the large negative ions favors ionic. Large charge on both ions will favor also covalency. And if the positive ion has not the electronic configuration of noble gas, okay, in this case the polarization will tend to the covalency. Why I explain the polarizability? Because in the organometallic bond we have bond between a metallic ion M and ligand L, and the bond is M plus, okay, is M plus L minus. That means the ligand is donor of the electrons and the metallic ion is acceptor of electrons. This is the ionic model and not the polarization or the polarity. The polarity is the inverse. When the ligand gives electrons to M, it becomes L plus. I talk about the ionic model. In organometallic chemistry, we are not interested about the size of M and the size of ligand because we have a lot of exceptions. For this reason, we study only the donation of L to M, and we study the electron density on M. So the stability of the bond Ml depends on the donation of L and the electron density around M. We will study the main Lewis-base ligands, and we start with the non-carbon donor ligands. Are ligands that have one or more lone pairs of electrons that can be donated into empty orbitals on the metal center. For example, the phosphine PR3 has lone pair on P that can be donated to the metal center. The donation of the ligand depends on the electron density on P and on the electronegativity of P. So to have a bond Ml, we need two conditions. The donation of one or more lone pairs, for example, and the most important, that we have empty orbital on the metal center. And the term empty orbital does not mean we have a location vacant. In organometallic, a metal center has empty orbital if its electronic counting is not saturated, is not equal to 18. For example, a metal center with 16 electrons has empty orbital. The second type of ligands are the halides donors, and in general, we use halides because the bond M halide is weak, so M can release the halide easily. And we have F minus, Cl minus, Br minus, and I minus. Since I minus is the strongest nucleophile, so the bond Mi is the most stable in the family of M halides. And according to Lewis structures, we have 4 lone pairs. So we have several types of bond Ml. One lone pair from X to M, and the halide is 2 electron terminal donor. The halide may be bridging between 2 metal center and is 2 electron donor to each metal center, or 4 electron donor in total, so 4 electron mu bridging, or the halide can be bridge between 3 metallic center and is 6 electron mu3 bridging, or 2 electron donor to each metal center. Halides are anionic donor in general of 2 electrons to the metal center. The electronegativity of halide is relatively high, so is not a good sigma donor ligands. By theory, the halide can act as sigma donor and as pi donor ligands. This is related to the structure of halide. For example, if we have a bond MCl, the Cl is Cl minus. So by Lewis, we have 4 pairs of electrons, and the geometry of this ligands, of these orbitals, is tetrahedral. And we have 4 sp3 hybrid orbitals. And the metal center has orbitals in all directions. So, from this lone pair to the metal center, this is a sigma donor. But we have lone pair that can be donated to the metal center by the pi method. So Cl by theory or halides are in general and the common case are sigma donor and can act also as pi donor. The fluoride is not a good ligand. Why? Because F minus or F is the most electronegative element in the periodic table, so it cannot donate these electrons easily to the metal M. And as we said, iodide of lowest electronegativity in the family of halide is a good enough donor and has enough orbital extension to act, for example, as 2 electron sigma donor or 2 electron pi donor or 4 electron sigma or 4 electron pi donor. But the most common case is the 2 electron sigma donor. To note that in organic chemistry, the bond CCl is sharing of electrons between carbon and chlorine. So the halogen are treated in organic chemistry as neutral ligands and are electron withdrawing. So the electron shared between carbon and Cl are attracted by Cl since Cl is more electronegative than carbon. But in inorganic and organometallic chemistry, the type of bond is quite different from that in organic. So the bond Ml in organometallic is donation of electrons from L and acceptance of electron to M. So the halides are treated as anionic ligand and not good donor of electrons. When halide act as bridging ligands, as we said, they donate 2 electrons to each metal center, and we have several types. We have mu2, the halide is bridge between 2 metal center, or mu3 between 3 metal centers. In the family of oxygenated ligands, we consider alkoxide RO-, which is by theory 2 electron donor terminal to the same metal, or 4 electron donor to the same metal. It can be bridging, 4 electron donor, so 2 electron to each metal center, and triply bridging. The oxide, the second type of oxygenated ligand, is the oxide which is 4 electron donor terminal, or it can be in rare case 6 electron donor terminal. It can be bridging between 2 metal centers, so 4 electron donor in total, 2 electron donor to each metal center. The third type is the ethers, like THF, which is 2 electron donor, and this is typically a weak donor. For this reason, in some organometallic reactions, we use the THF as main solvent because it's a weak donor and it cannot bind to the metal center. The carboxylate RCOO- is anionic, 1 minus a charge, but it can be 2 electron donor terminal if it's hapto-1, or it can be 4 electron donor if it's hapto-2 terminal. And pay attention, in the case of carbon of pi systems, the rule of odd and even number, which is x plus 1 electron donor or x electron donor, is only applied for the carbon of pi system. In this case, the carboxylate is a mu2, anionic, and 4 electron donor. By the same way, the carboxylate can be mu bridging, so the charge of the carboxylate 1 minus is divided in the 2 metal center and is 2 electron donor from each oxygen. We have other oxygenated ligand as acetoacetonate, known as ACAC, which is 2 electron or 4 electron donor. In the family of the sulfur donor ligands, we consider thiolates or mercaptide Rs-. It's 2 electron or 4 electron donor terminal to the same metal, but thiolates are known to be bridging ligands between 2 metal centers, so it acts as 4 electron donor. And in the rare case, it can be triply bridging 6 electron donor. Rs- are highly reactive, so they are easily oxidized to the form RSSR. As we said, thiolates are powerful bridging ligands, especially for the low oxidation state metal centers. And according to their lower electronegativity relative to oxygen, thiolates or mercaptides are considered as good sigma donor. The second type of the sulfur ligand is sulfide S2-, which is by theory 4 electron donor terminal or 6 electron donor terminal. So M double bond S for electron terminal and M triple bond S is a 6 electron donor. But this configuration are rare case. Sulfide, the most common case for sulfide is the bridging sulfide, mu2 to 2 metal center and 4 electron donor in total, or mu3 bridging, 6 electron donor, or quadrupole bridging, mu4, 8 electrons donor. Sulfides and thiolates, as we said, are extremely effective bridging ligands and they play important role in bioinorganic chemistry. For example, the ferrodoxins or the FeS cubane, these forms are known in bioinorganic for their biological activities. Family of nitrogen ligands, we consider the alkylating amines, which are not good sigma donors due to the structure of alkylated amine. The structure, the figure of repulsion, is tetrahedral and the donation of alkylated amine is from the free lone pair. Since we have overlap between the orbitals of nitrogen and carbons, and that makes NC bond short, so the alkylated amine would not be a good sigma donor due to the steric effect. In other words, the lone pair of nitrogen is hidden due to the steric effect of the alkyl groups. Chelating amines such as alkyl diamine have less steric problems, so they are considered as better ligands for transition metal. But the problem of the chelating amine is their susceptibility to oxidation. Consider, for example, ethylene diamine, which is primary amine from the two sides. This chelating amine can bind to a metal center as 4-electron donor, but the bond Mn is stable, but the structure in total is not stable because chelating amine primary can be oxidized, can do oxidation to form the diamine complex. So tertiary amine such as tetramethyl ethylene diamine TMEDA are quite stable and not easily oxidized. The most famous neutral nitrogen donor ligand is bipyridine or bipyridyl, and the abbreviation is BiPi. Bipyridine is 2-electron donor from one nitrogen or 4-electron donor from the two nitrogens. Phenolphthalein, Phen, is a more rigid version of bipyridine that forms even stronger metal ligand bond. The complex with bipyridine, such as ruthenium bipyridine 3,2+, are well known in the photoredox chemistry, and the bipyridine ligand can stabilize multiple oxidation states on the metal center. For example, consider chromium bipyridine 3,3+, and the chromium bipyridine 3,1-. Bipyridine can stabilize the oxidation state in these two complexes. That some transition metals can be made to have negative oxidation state, like, for example, in inorganic chemistry, the most famous examples are Ta1- and HF2-, hafnium. But these compounds are typically very reactive, air and water sensitive. In this complex, the chromium has oxidation state 1-. Chromium 0 is known to have the structure D6 or S2D4. So the orbital D is filled, and it can pass to the most stable state, which is half filled. Before we said that chromium S2D4 become S1D5 because this electronic configuration is more stable and the orbital d5 is half filled, which is relatively stable. It can receive another one electron to have also the stable structure S2d5, and this is the structure for chromium 1 minus. Amides R2N minus are strong base and nucleophile. They can act as 2 electron donor of the first lone pair terminal or donation of the 2 lone pairs to the same metal, so 4 electron donor. Amide ligand can act as 2 electron donor to one metal and 2 electron donor to another metal, so it's 4 electron bridging donor. The donation terminal 2 electron or 4 electron depends on the structure of amide. The lone pair of amide is according to the DFT calculation, density, functional theory, are about 2 electron volt higher than in alkoxide. That means the lone pair of amide is more donor than in alkoxide because it's less stable. So amide are considered as good sigma donor, better than alkoxide. Amides complexes are prepared by direct reaction between, for example, metal halides with lithium amide to give amide, and the degree of substitution depends on the nature of the R groups used and on the halide metal used. Amide 2 electron donor or 4 electron donor, we said it depends on the geometry of the amide metal. And as you know, when we prepare organometallic complex, the geometry is obtained by X-ray diffraction on crystal. Amide is donor 2 electrons. When amide is donor only 2 electrons, the R groups conserve their ratio selectivity with respect to the structure. So the geometry is pyramidal geometry. N, lone pair, R, we have pyramid form. When the amide is 4 electron donor, 2 electron donor from the first lone pair and 2 electron donor from the second lone pair, it will change the geometry of the R groups with respect to the nitrogen, and in this case we have a trigonal planar geometry. 2 electrons from N to M terminal, and if the other 2 electrons make bond with the orbitals D, we will obtain M, N, R, R in a trigonal planar geometry. So in the pyramidal, we have sp3-like hybridization, and in the 4 electron donor system or the trigonal planar, we have sp2-like. We could not predict the donation of amide ligand 2 electron donor or 4 electron donor. The experiment will justify or will prove this donation. But in general, the pyramidal geometry MNR, or it can be seen from the second side, lone pair NRR, so this is the pyramidal geometry, is the most common donation. In some complexes, we determine that the metal center is 18 electron complex, and then if we need 2 more electrons, we can use the trigonal planar form of amide 4 electron donor. 2 electron donor or 4 electron donor of amide depends on the nature of the metal center M. Alkyl imido ligand or nitrene ligand Rn2 2-, and according to its structure, it can be 4 electron donor or 6 electron donor terminal, or 4 electron mu2 bridging, so 2 electron to each metal center, or 6 electron mu3 bridging, 2 electron to each metal center. Imido or nitrene ligand, 4 electron or 6 electron donor, by the same way as in the case of the amide, the donation of the imido or the nitrene depends on its structure obtained with the metal M. And to note also that the structure is obtained by experiment. In the band form MNR, imido is 4 electron donor, and in the linear form MNR, the imido or the nitrene ligand is 6 electron donor. This is examples of metal nitrene complexes in the linear form or in the band form. To note, if you use in this case the nitrene 6 electron donor, you should realize to write the bond radium and methyl in the linear form. Borate ligand, abbreviated as Tp-, is anionic 1-, tridentate, so 6 electron donor, and it makes the coordination via the 3 lower nitrogens, is a moderate donor but is a bulky group, and its bulkiness increase with the large R groups. Due to the higher nitrogen electronegativity, Tp- is not considered as good enough as Cp ligand. Thus, when Tp- is bound to M, it looks like a tripod structure. Tp- ligand has become extremely popular in the last decade and is sometimes called the inorganic Cp ligand. At the end, we have a list of some biological important N ligands. For example, imidazolate, pyrimidine, purine, and porphyrin, and these ligands are well used in the organometallic complexes for biological activities known in the bioinorganic.